Hello, welcome back to Chapter 6, Part 3, and this will be the final video for this chapter. And what we need to do for this particular video is we're going to go back and take a look at all of the previous types of forces that we've seen, both in Chapter 5 and in Chapter 6. So we'll just get the list going here. So of these three forces, what we need to do is we need to figure out how any of these forces can generate circular motion. And so we're going to be tying in materials from Chapter 4. And in Chapter 4, we had a derivation where we put everything together in terms of traveling around a uniform circular path of radius r with a constant speed of v. We called that speed because we would constantly be changing the direction of our velocity vector. But regardless of where we are on that circle, the only way that we could maintain that circular motion was if we had an acceleration vector pointing towards the center of the circle, hence the name centripetal acceleration. Well, we can take this equation from Chapter 4 and combine it with Newton's second law of motion, which is just another equation, specifically by importing the expression for centripetal acceleration, because Newton's second law doesn't care what the acceleration is. It just knows that if you apply mass to that acceleration term, there has to be a force which is generating that acceleration. And so by taking our centripetal acceleration expression and rewriting everything, we now have a way of measuring the centripetal force for a given system. Now, everything over here is basically a product of applying this centripetal force to our mass. So just like with Newton's second law, if we apply a force to a mass, then that mass will start to accelerate at a given rate. Well, we now have a force, which we're calling a centripetal force, which we're going to apply to a mass, and the result is that it will start to travel around a circle of radius r with a specific speed of v. So everything here was just our centripetal acceleration term. It is our job now to figure out what force is causing all of this to happen. So we need to go back and we need to look at systems where we have an object that's moving in a circle and ask ourselves what force is causing that object to move in a circle. And we're just going to go ahead and go down the list of our candidate forces to see which, if any, could cause centripetal motion. And spoiler alert, all four of them can cause circular motion. So this is why we need to look at each one of them individually. So we'll go through a discussion for each of these forces pertaining to a circular motion problem, and then that'll bring us to the end of the Chapter 6 material. So for gravity, we have two ways that we've been utilizing gravity in our physics problems. We have force of gravity can equal mg, and this was any time we were working at the surface of the Earth, or at least relatively close to the surface of the Earth. But then we had another case scenario where if we got really far away from the Earth, or we didn't even necessarily have to be dealing with the Earth. We could be dealing with any two masses out in the universe, and there would be a gravity force between them. And so I guess we could say everywhere else underneath this expression, but so at surface of Earth, and we'll say everywhere else. But this equation said for any two masses separated by a distance r, we can find the force of gravity between them. Now, of these two cases, which one is going to result in circular motion? Well, if I have a rock and I drop it straight down to the ground, well, that's just motion along a straight line. There's no circular motion occurring there. So we don't get to use this stuff. But everything about this second equation says we could take something like the Earth and have a satellite that orbits around the Earth. In fact, we've already had a similar discussion to this. And now that we have the Earth has a certain radius, r of e. We can say that the rest of this distance would be the altitude that our satellite is above the Earth. And so the r value, which is actually the center to center separation distance between the masses, if you remember that part, that r value has to be radius of Earth plus altitude of the satellite. And then the two masses that are involved would be the mass of the Earth and the mass of the satellite. So our gravity force between the Earth and the satellite would be big G, mass of the Earth, mass of the satellite, divided by the distance between their centers squared. Okay, well that's the force of gravity acting between these two objects. How does that cause circular motion? Well, just like the picture that we had over here, in this case we said that the gravity force always pointed down. Well, why is it always pointing down? Because that's where the Earth is. And the mass of this ball or rock or whatever it is being attracted to the Earth. Hence the reason our gravity force is pointing down. Well, in terms of the satellite is going to have an attractive force of gravity pulling it towards the Earth. But the direction of that attractive force of gravity is pointing towards the center of this circular orbit. So if I were to draw the satellite at some other location in its orbit, and remember for this circular motion, the satellite has some speed that is trying to carry it outward. But as it tries to travel outward, gravity grabs hold of it and pulls it back in towards the Earth. And this is going to continue happening all the way around until we've completed a full circular orbit of constant radius r. So no matter where we are in our circular orbit, our gravity force is what is causing the circular motion to occur. That means I can set the gravity force, which we just put together, equal to the expression that we had right up here for centripetal force. So let's see what it looks like when we put these two together. We want f of c equal to f of g. So we're going to set these two expressions equal together. Our f of g, big G, mass of Earth, mass of satellite, divided by the separation distance squared. That has to equal the centripetal force. Our centripetal force is using just one mass. And over here we had two masses. So which mass are we talking about with the centripetal force? With the centripetal force, the mass that we are going to be discussing is the mass that is actually traveling with a speed of v at a radius of r. And so that is going to be the satellite. So we now have mass of satellite times our centripetal acceleration term, which is v squared over r. And we now have an expression that describes the motion of this satellite as it orbits around the Earth. Now, we do need to do a little bit of cleanup with this expression. There's usually always some amount of cleanup that has to be done with any kind of mathematical expression. But the first thing we should notice is that both sides of the expression have the mass of the satellite. And so the mass of the satellite will cancel out. And what this means is that the mass of the satellite doesn't matter. I can have a very small satellite, like the first satellite up in orbit was Sputnik, and that was only a few kilograms, versus having the International Space Station, which is literally tons of material orbiting around the Earth. But whether it's Sputnik or the International Space Station, the mass of the satellite doesn't matter. Once we get that up into orbit, it's basically going to get a free ride around the Earth by balancing out the gravity force, which is constantly trying to pull it in towards the Earth, versus the velocity, which is constantly trying to carry it out into space. In a previous video, we discussed this as perpetual free fall. So the satellite is constantly falling towards the Earth, but at the same time, it's constantly flying out into space. And so we never really change the altitude of that satellite, yet we're always falling. And because the satellite is always falling, again, if we use the International Space Station as an example, the International Space Station is constantly falling, and so everything inside of it is falling at the same rate, and so everything looks like it's floating, or as a lot of people do, they use the incorrect term of weightlessness. But to be weightless means that you have no weight, and that is not correct. Well, a little bit more cleanup here. Now that the mass of the satellite has been removed, what is left is the velocity of the satellite, the radius of the satellite. We have big G, mass of the Earth, and then we have the center-to-center separation distance. But keep in mind, the center-to-center separation distance that we came up with, that was the full radius of the circular path that we were traveling around. And so that R value right here is actually the same as what this combination is equal to. So we'll go ahead and remind ourselves, this is the value of R, but both sides of this equation are using the same value of r. It's just that one side has an r squared value. So there's the other bit of cleanup that we can do, is we can cancel out one of the r values, and we're left with an expression that tells us exactly how fast our satellite would have to be traveling around the Earth given its radial position. This does depend on the mass of the Earth, but we don't have to limit ourselves to the Earth. Maybe we want to put a satellite in orbit around the Moon, or around Jupiter, or Mars. In that case, we would use the mass of that specific planet or moon. We would figure out at what radial value from the surface, or excuse me, the center to center separation distance between our satellite and that planetary body. And that will tell us how fast our satellite has to be moving so that it doesn't crash into that planet. But at the same time, we want to make sure that the satellite is not traveling too fast, otherwise it will fly out into space. So again, there's that very delicate balance between the force of gravity pulling the satellite down and the velocity wanting to carry that satellite out into space. And this equation is what tells us exactly what that balance needs to be. And this is pretty important for us because we have literally thousands of satellites that are buzzing around the Earth, but some of those satellites are what we call geosynchronous satellites. And if we take the word geosynchronous and break it down, well, the geo in the front means Earth. Synchronous means at once or at the same time. And so these are satellites that are specifically put into orbit such that they maintain the same relative position above the Earth at all times. So this satellite up here that I've drawn as a square, maybe that's a cable TV satellite. And what I've drawn here as another rectangle, maybe that can be South Dakota. And so you want to be able to watch your favorite cable TV shows at any time using this satellite TV. Well, the satellite can only beam its information along a line of sight. And so only in that area, or only about this surface of the Earth will that satellite be able to beam down its signal. Now, if that satellite were moving too fast, eventually the satellite would carry itself outside of that line of sight, and we would no longer be able to pick up the signal that the satellite is sending. If the satellite was moving too slow, then the Earth would spin out of range, and we would no longer be able to receive the signal from the satellite. So we need to place this satellite at a location above the surface of the Earth such that as the satellite goes around, it's constantly keeping track with us on the surface of the Earth. Well, we go around every 24 hours, and so we would have to have the satellite travel around once every 24 hours. So at what center-to-center radius would that satellite have to be placed at, and at what speed would that satellite have to be traveling such that we can accomplish this 24-hour orbit, because then our satellite would remain relatively fixed above our heads, and it would constantly be beaming down a signal that we could pick up, and then we don't lose our favorite show, unless there's a big thunderstorm or something which is interfering with the signals. Well, this is a perfect problem for the centripetal motion that we came up with. And we said that this was the equation that was going to allow us to balance between how fast we were traveling and the center-to-center separation distance. But I've asked for both answers, and we only have one equation. So how do you get a solution for one equation, two unknowns? Well, I suppose you could just plug a value in, just plug a random value in for V or for R, and you would get an answer for the other one. But how do you ensure that the combination that you have randomly chosen is going to result in a 24-hour orbit? So to do that, we actually have a second equation that we can bring into the discussion, and that is one that we call period of motion. So the period of motion, capital T, this is the amount of time that is required to complete one event. In this case, the event is one complete orbit around the Earth. Well, we already know what that is. It's 24 hours. And we might want to convert that to seconds, just because that's the unit that we need to be using for all of our physics. But how do we calculate the time that is required to go around this path? Well, for the sake of argument, we're going to assume that this satellite is traveling in a perfect circular orbit. That's not exactly true. All orbits are actually elliptical, but we're not quite there in terms of the math yet. But for a perfectly circular path, you have to travel a displacement of 2 pi r. Or a better term might be you have to travel a distance of 2 pi r. And that's just the circumference of the circle. If we divide that by the time that it takes to complete that one path, hence the period of motion, well, distance over time, that's speed, that's velocity, and that's a term that we have up here. But what do we have here? Well, it's a second equation that involves both the speed of the satellite and the center-to-center separation distance. And now that we have two equations, two unknowns, we're now going to be able to solve specifically for one solution set that will work. All we need to do is plug in the 24-hour time constraint for our period of motion, and again, it needs to be in seconds. But from there, you can do a combination of the two equations, and you can independently solve for the required speed of the satellite. You can also independently solve for the center-to-center separation distance that would be required for that orbit. So lots of stuff that we could do with that, probably more than you were expecting for circular motion and gravity. But now we're going to move on to the second of the forces on our list, which is the normal force. Now, for a normal force, we've only really seen example problems where we have a mass that's sitting on a flat surface or maybe an incline. And in either case, we could produce a sum of forces that would tell us what the normal force needed to be. And I'm just going to go ahead and skip ahead and write those out. For this first example, the normal force would equal the weight. For the second example here, it would be mg cosine, and we can go back into our notes and see where these values are coming from by using those sum of force techniques. But we want to see if a normal force can be used for circular motion. So we'll come down here where got a little more room. All right, so you're going to take a job as a daredevil, and you're going to ride a motorbike through a loop-the-loop. And I'll go ahead and I'm just going to draw the bike at some choice locations as we go through this loop. So we're traveling this way, and then as we enter the loop-to-loop, we're going to start changing the direction of the speed of the bike as we go all the way through the loop. But that means that if we're going to be traveling in this circular path, there has to be a centripetal force that is pushing the bike towards the center of the circle. Well, let's see what that might be. And we'll focus at the bottom portion of the track here. At this particular location, you and the bike will have some amount of weight that is associated with you. So we have mg. And as your weight presses down on the track has to push back on you with a normal force. And what we are looking for is a force or combination of forces that points towards the center of the circle to provide a centripetal acceleration. So at the bottom of the track, let's just do a quick sum of forces. And at the bottom of the track, I am going to choose up to be the positive direction, mainly because that's the direction that I see the centripetal acceleration pointing in. But if I do a sum of forces, I see the normal force is pointing up, the weight is pointing down, and those two forces together have to be responsible for whatever centripetal acceleration the bike and the rider are experiencing. And so it's not just the normal force, but it's a combination of the normal force and the weight that are causing the centripetal acceleration. So let's get a value for the normal force. I would have to add the weight over to the other side, and so we would have mg plus AC. Or if we want to assume that we have uniform circular motion, we could say that A sub c equals v squared over r, and so the normal force would equal mg plus v squared over r. Now we'll hold on to this answer here, and we'll come back and revisit this, and we'll see just what the consequences of this are, because now we want to look at the other locations. We want to look at what's happening on the far right side of the track, what's happening, what's happening at the very top of the track, and what's happening at the far left-hand side of the track. At the far right side of the track, oh, there we are. There's the far right side of the track. And gravity, well, gravity still has to point down. Just because we're traveling through this loop-to-loop does not mean that gravity is going to change the way that it behaves here at the surface of the Earth. Gravity's still going to point down. Yet there has to be some force that causes a centripetal acceleration. And the only thing that I can really think of is the fact that the bike is still in contact with the surface of the track. And as long as the bike is in contact with the surface of the track will be pushing on the bike with a normal force. And that normal force has to be perpendicular to the surface of contact. So now we'll try that sum of forces again. And because the bike is at a different location, because my forces have been drawn in different directions, I am validated in saying that this is a completely different physics problem. And I'll let my reference frame be in the direction of the centripetal acceleration again, because I would prefer to have the acceleration term be positive. Well, the weight is no longer contributing to the actions that are occurring along the centripetal motion direction. In other words, I need forces that are acting along the radial direction, and those will be the forces that contribute to the centripetal acceleration. mg is pointing in a completely different axis. It is not going to contribute. So we'll come down here and we'll start putting together a sum of forces. Sum of forces along the x direction at the right-hand side of the track. The only thing that I have in the x direction is the normal force. That's it. So it's responsible for taking the mass of the bike and the rider and accelerating it at a rate of a. Or we can rewrite a sub c as v squared over r. And now we can kind of do a comparison here. Well, what's happening to the normal force? Since we've climbed up the track, our normal force has actually diminished a bit. Because up here we had g, and remember the sign on g is the sign on the number. This is a positive g right here. This is 9.8 plus some construct here which cannot be negative. Now I've got a square term up here that can't be negative. R is the measure of the radius, that can't be negative. But then we drop down here and now I just have m v squared over r. So our normal force has weakened a little bit. Well, let's take a look at the top. At the top of the circle, There's the top of the circle. I'm going to get rid of this right here just for now, and this, so we don't get ourselves confused. At the very top of the circle, we have the weight of the rider and the bike pointing down. And as long as the bike is still in contact with the track, as long as the bike is still touching the track is still going to push on the bike, normal to the surface of contact. And so we have a normal force. In terms of centripetal acceleration, I now have both the normal force and the weight pointing towards the center of the circle. If I put everything together with a sum of forces, new position on the diagram, new arrangement of forces. So I will introduce a new reference frame. I will let down towards the center of the circle be the positive direction. And what that means is that I have the normal force plus the weight contributing to the centripetal acceleration. So it's similar to the equation that we had for the bottom, but there's a difference in the sign notation. And that difference in the sign notation is going to affect how the normal force is represented. Now, instead of having mg plus v squared over r, we have v squared over r minus g. So what's happening now? Well, from here to here, our normal force became weaker, but now from here to here, the normal force has become even more weak than it was before. And when we're going through this loop-de-loop, the real concern is being able to travel fast enough as you go around the circle such that you don't fall. You want to remain in contact with the track at all points. So we never ever want our normal force to go to zero. We always want to make sure that the bike is touching the track. Well, we have one more location, which is the far left side. And by now you can probably tell there's not a whole lot different about the left-hand side compared to the right-hand side, because we're still going to have gravity pointing straight down. We want the bike to be in contact with the surface of the track, so that means the track needs to provide a normal force, which is pointing towards the center of our circle in the direction of our centripetal acceleration. I'm going to let the center-seeking direction be the positive direction for my sum of forces. But the only force in the x direction is the normal force. The weight is now in the other axes, and so it's not going to contribute to the math. Here we go. We'll fill in that sum of forces. We have the normal force, and that's it. So that's responsible for the centripetal acceleration. And there we have it. So the normal force at the right side and the left side are actually equal to each other. Because in both cases we have mv squared over r, mv squared over r. And then the next thing that would happen, since we are going around in a circle, is that we would eventually end up back at the bottom of the track again. which would reproduce the same expression that we have at the bottom of the track, way up here. But this tells us something kind of interesting, since the normal force is constantly changing as we go around the circle. We'll take a little side discussion here. Let's say that you were in the bathroom and you decide that you're gonna weigh yourself. You're gonna step on a scale. So you step on the scale. Your weight presses down on the scale. In response, the scale has to push back on you with a normal force. And we say that the scale is measuring our weight, but that's actually incorrect. The scale is measuring the normal force that is required to support your weight. And you're probably thinking, what's the difference? If I do a sum of forces here, normal force equals the weight, it's measuring the weight. Well, let's say you stand on this scale and you're holding a large box, a very heavy box. You stand on the scale now. Is the scale in fact measuring your correct weight? And the answer is no. The scale is going to measure the combination of your weight and the weight of the box. So it's not just measuring your weight, it's measuring everything. So the normal force, obviously if you were to get on that scale and maybe you start jumping up and down on the scale, you're going to see that needle bouncing back and forth all over the place. It's not going to give you a correct register of what your weight is. And that's because the scale is constantly measuring the counter force. And if you jump up and then jump down, well, that's going to momentarily change the amount of force that presses down on the scale, which is going to change the amount of counter force that the scale has to provide. So in every one of these situations, we can ask the question, how do you feel? Do you feel light? Do you feel heavy? Or do you feel like you normally would? Because on the bathroom scale, you're supposed to get on the scale and you're supposed to stand still, give the needle a few seconds to bounce back and forth, and then you measure your weight. In this case, we can take that normal force and we could relate it to something called apparent weight. So essentially, how do you feel? Do you feel light? Do you feel heavy? Do you feel normal? So obviously not the same normal here as normal force, but in the first case here at the bottom of the loop, not only do you have mg at the bottom of the loop, we have mg plus v squared over r. So not only do we have mg, but we have the added effect of the centripetal motion. And together, this is going to make you feel very heavy when you get to the bottom of that loop. When you get to the top of the loop, we have mv squared over r minus g. The difference in these two values is actually the smallest of all of the values that we had. And so here you're going to feel extremely light. So light that you might even feel like you're going to fall down. And then at the two sides, at the right and left, We can't actually use these expressions to tell us how we feel because at those locations, well, your weight is pointing down. And so at those two locations, you should just feel like you normally would in terms of your weight. But at the top and bottom is where things start to feel really strange. And there's a similar effect that you can experience on a roller coaster. As you go through the the peaks and the valleys of a roller coaster, as you approach the top of the roller coaster, the tendency of your body is to continue going up, whereas the cart is going to start to drop out from underneath you. And so you're going to feel very light at the top. Versus at the bottom of the track, the tendency of your body is to continue moving down, whereas the cart wants to move up. And so the cart physically has to push harder on you to start moving you upward. And as a result, you feel extremely heavy when you get to the bottom of the roller coaster track. The same thing is happening here with the loop-de-loop. So what I would like to do for the last part of this normal force discussion is ask ourselves for a loop-de-loop of radius 10 meters. How fast do you have to go so that you can safely make it all the way through the loop-de-loop? And keep in mind the most dangerous spot in this whole daredevil feat is going to be right there at the top. This is where you want to make sure that you're not losing contact with the track. This is where you want to make sure that this doesn't happen. So let's go to the top of the track, which was right here. Let's take that equation that we have. We have normal force equals m v squared r minus g. Let's put that up here. Normal force equals m v squared r minus g. Now I have my r value. I have my g. I know what that is. I don't know the mass of the rider and the bike just yet, but you know what? I'm not going to give that, because whether it's you or me or somebody else that is trying to attempt this feat, is the mass going to matter when it comes to figuring out what that speed should be? And a lot of people would say, well, yeah, it should matter because the mass is in there. All right, well, if we want to safely make it through this loop, then I pose the question, what is the absolute minimum value of normal force that you can have and still remain in contact with the top of the track? And we know that having a normal force that is equal to 0 is going to be bad for us, because that means that we're no longer in contact with the track. But how close to 0 could you get? You know, could you have a normal force of 1 Newton, 0.1 Newton, 0.01 Newton? You know, every one of these, as long as it's not 0, technically means that we're still in contact with the track. Well, why don't we press our luck? And let's say we're right on the verge of falling. Okay, we're just barely in contact with the normal force, we're just barely in contact with the top of the track. In fact, our ability to measure that normal force is so small that it may as well be 0. Now, why do we want to do that if we said that that is such a bad idea? Well, this brings us to the most extreme case scenario, which is that we fall. But by including a 0 into the math, that makes our job so much easier because it's our job to figure out what is that minimum speed going to be. And right here, if we let the normal force equal 0, then we can say this is the speed at which we're going to lose contact with the track. So let's make sure we're going faster than that. And then we have our answer. But setting this equal to 0, what happens? Well, we can divide the mass out of each side, because that's going to be the first step in getting v by itself. I'm going to have to start moving terms over. But if I divide the mass over, 0 divided by mass is still 0. So the mass doesn't matter. Again, whether it's you or me or somebody else that's attempting this feat, everybody has to achieve the same minimum velocity to get through this loop-to-loop. That's what this means. And we now have our answer. We'll do a little bit of rearranging here with the algebra, but v is going to have to equal root gr plus minus. And what did we say we had for a radius? 10 meters. I think I had it down here somewhere. Yep. Radius of 10 meters, how fast do we have to go? So we'll plug in 9.8 and 10. And that's basically square root of 100. It's a little bit less, but we'll put that into our calculator. Square root of 9.8 times 10. Square root is 9.9. We have to have a minimum speed of 9.9 meters per second to safely get around that loop-to-loop. But I would say, for safety, maybe we bump that up to 10 meters per second, or even faster. Faster would always be better. But to travel faster around the circle in every case would mean to increase the normal force. And the more we increase the normal force, the more we increase that apparent weight. The more we increase that weighty feeling of being heavy. All right, so I think that's enough for the normal force. So we've definitely seen how the normal force can contribute to centripetal motion. The next one that we have is the tension force. This one will go pretty quick because the tension force and the normal force are fairly similar to one another in the way that they operate. The tension force is just basically how we're gonna get things moving when they're not in contact with another surface. But let's do an overhead view. So we're going to look down on a tabletop where we have a mass that is tied to a rope, and that mass will be swung around in a circle, a horizontal circle, by a speed of v, and the length of the rope will be the value of the radius of the circle. As such, there will have to be a centripetal acceleration, but a centripetal acceleration means that there has to be a centripetal force. We already know from our discussions with tension tension must pull away from the body of contact. So we have this rope attached to the mass. That tension force has to pull away from the mass, and that tension force is pointing in the same direction as the centripetal acceleration. I'll go ahead and define a reference frame. Positive x will be in the direction of the centripetal acceleration. All I have for forces in that direction is the tension force, so that is responsible for accelerating the mass at a rate of a. And we're done. Now we can apply this to a problem. Let's say your mass is 2 kilograms and the rope, if you ever go out and buy rope, especially if it's like climbing rope, it's usually rated for a certain amount of weight, and you should not exceed that rating, otherwise it could break, and then you have a lot of problems after that. But let's say this particular rope has a rating of 2,000 newtons. So this is the maximum value of tension that rope can support. If we exceed that, the rope will break, and if the rope breaks, then that rock is going to travel off in that velocity direction, whichever direction it happens to be in. So how fast can we get this rock moving around its circular path and not break the rope? Well, if I'm trying to maximize the velocity, then I'm pretty much maximizing the tension as well. So let's go ahead and put in the maximum tension into our equation. We'll rearrange to solve for the maximum velocity. And so that means we have to multiply by r, divide by m, and take a square root. And technically this has become speed because we're constantly changing the direction of our velocity vector. But now we're ready. We'll plug in our numbers. We have a maximum tension of 2,000. Oops, I forgot to provide a radius value. We'll say 1 meter. Our max speed is then square root of 1,000. Get my calculator app back open. Square root of 1,000 is 31.6 meters per second. If we go any faster than that, the rope will break. If we go any slower, well, then the rope will not break. However, if we go slower than this, a reduction in the velocity value will result in a reduction of the tension value. So if I only have a speed of 20 meters per second for this rock, how much tension force would there be in the rope? Well, we have our 2 kilogram mass. We now have 20 meters per second for the speed, and we have a radius of 1. And so 20 squared is 400 times 2 is 800. 800 newtons of force is what we would have for that tension. Now we can take this example further. We can do something similar to what we did with the loop-de-loop. We could take that same rock, and instead of swinging it around in a horizontal circle, we could swing it around in a vertical circle. And what this means is that at any particular location, whether we're at the the bottom of the loop or the top of the loop or one of the sides, we would still have tension pulling towards the center of the circle. That's the only direction that the tension force can point, because it has to point along the direction of the rope. But then we would have gravity to contend with at each location. In some locations, the gravity does not contribute to the centripetal motion. At other locations, it does contribute to the centripetal motion. But I think you can see here just how similar this situation is to the centripetal motion of the loop-de-loop problem. At each location, I would have a centripetal acceleration that points towards the center of the circle, and I would need to set up sum of forces at each location. And I'm just going to go ahead and write these out. We've basically already seen these written out once for the normal force case scenario. But at the bottom of the swing, we would have tension minus mg equals mac. At the right, the weight does not contribute to the direction of the centripetal motion, and so all we have is T equals mac. At the top of the swing, we have everything pointing down. And for each one of these expressions, I'm assuming towards the center of the circle to be the positive direction. So in this case, for the bottom, towards the center of the circle is the positive direction. For the right-hand case, towards the center of the circle is positive. For the top, towards the center is positive. Remember, for each one of these cases, it's a different physics problem, and so we can set up our reference frame however we want for those particular locations. But at the top, we get T plus mg equals mac. And then at the left side, we get just T equals mac. And then you can fill in for a sub c equals v squared over r for each of these scenarios. And basically, you're just reproducing the equations that we had for the loop-de-loop, only now instead of normal force, you would have tension force. So as I said, they're very similar in how they work. But obviously, in one case, you've got a rope. In the other case, you have one object that's pushing against another and causing that circular motion. Okay, last one. Last force to consider for centripetal motion, and that is friction. So for friction, again, I want to consider an overhead view. Let's say that you are on the interstate. So we're looking down on your car. Here we have your headlights, and you're traveling with a constant velocity, but then you decide to take an exit, and this will be one of those circular exits that go around like this and then probably cut over or under with some kind of a bridge. But as you take this exit, you're traveling through this circular path of R, and we'll go ahead and maintain that the velocity and the radius are uniform so that we can use our centripetal motion expression. And, well, how is it that you're actually able to travel through that circle? And Your answer would be, well, I just slightly turn the wheel, and that allows me to travel. But that's not an answer to the question. If you're going to travel in a circular path, there has to be something that is causing you to accelerate towards the center of the circle. And that means there has to be some force present. Now we can go through the list of candidates. We can say, well, is it gravity? No, gravity's not going to pull you towards the center of the exit that you're traveling on. In fact, if we if we draw kind of a side view, so now we're gonna look at the back side of the car. So imagine the car is driving into the page. And then we've got the radius of our exit here. And we have to have some kind of centripetal acceleration. So this is our side view. This is our overhead view. Oops. Here we go. So from the side view, we can see that, yeah, there is gravity, but which way is it pointing? It's pointing down towards the Earth. It's not pointing in the direction of the centripetal acceleration. So gravity is not the cause of your being able to take that exit. At the same time, because you have your weight pointing down, the weight of the car presses down on the road. The road has to push back with a counter force, which is a normal force, and that is not pointing in the direction of the centripetal acceleration. So it's not a normal force. And last I checked, there were no ropes or chains or anything else that I have to connect my car to in order to be able to travel around this circular exit. So tension is not a candidate. All that leaves us with, in terms of the forces that we've considered, go back to the list here, if I can get back up there. Maybe. Here it is. Okay. All that leaves us with is friction. That's the only thing that it could be. So let's talk about the friction. And I'm gonna use this side view to help us with this idea. Well, actually, I take that back. Let's go to the overhead view. As we are traveling in our car, imagine that it's a very, very snowy, cold day, and the roads are very, very icy. And we've all been there at some point where we're driving just a little bit too fast. We try to turn, and what happens? Well, we don't necessarily turn, we just keep going, right? So the tendency of our vehicle is to continue traveling in a straight line. We need to have some kind of force that pulls us towards the center of the circle. So back to the side view. The tendency is for our car to want to slide outward. And we need something to counteract that. Well, if the tendency of our car is to slide outward, if that is the intended direction that our car wants to travel, then that means that we need a counterforce in the form of friction to keep us from sliding out. And now this starts to make some sense. It is our tires as they essentially grip the road that provide us with a friction force that points towards the center of the circle. And it is this friction force that allows us to continue traveling towards the center of the circle. Otherwise, if we don't have that friction force, then it's off into oblivion or off into the ditch in the case of the winter weather driving. And so this becomes an issue anytime we take a turn. We have to have an adequate amount of friction available to keep us on the road. The question is, of the two types of friction, which one do we have to use? Do we use the static friction or the kinetic friction in this case? And I always take a poll in class. I can't really do that here with the video, but I present this situation to the class. I say you're driving along the road and you need some friction to hold you onto the road and keep you from sliding. So which one is it? Is it the kinetic friction or the static friction? And I have everybody vote. I have them raise their hand. I say one finger for static friction, 2 fingers for kinetic friction. And about maybe 80 to 90% of the class votes for kinetic friction because the car is moving. The car is in motion. Kinetic friction is the friction associated with motion. Makes perfect sense, except it's wrong. It's actually the static friction that keeps you from losing control. And you're thinking, well, how can that be? Static friction means we're not moving. Obviously, the car is moving. Well, let's consider a slightly different approach to the word static. Static means, in one sense, not to move, but it also means to remain the same or to not change. What is it about this motion of the car as it goes around the circle that we want to remain unchanged? And that is the radial value. As we go around this circle, we do not want the radial value to change. If it was, that would mean that our car is either physically moving towards the center of the circle or physically moving away from the center of the circle. And this case is bad because this is where you essentially lose control and you start sliding out into the ditch. This could happen if you were really cranking your wheel towards the center of the circle. You could end up driving through some kind of a spiral here, but that's not what we want. We just want the radius of our circular path to remain fixed. And so that means no moving towards the center of the circle, no moving away from the center of the circle. We want the car to remain static in terms of its radial position. And that means using static friction, because now think of it this way. As your tires make contact with the road, do you want your tires moving this way or that way? And the answer is no. Do you want your tires moving forwards and backwards? And the answer is yes. The tires were designed to do that. They're designed to roll forwards and backwards. Your tires were not designed to skid to the left and right. You're gonna cause damage to the tires and possibly to your car by doing that. So this needs to be static friction. And in terms of forces that are pointing towards the center of our circle, that is the only force that we have. And so our sum of forces along I will now define a positive direction as being in the direction of the centripetal acceleration. That's all I have is a friction force helping to maintain the centripetal motion. Now we have two ways of representing the static friction. We have regular static friction, which is essentially just equal to the applied force, but you'll remember we said that static friction only uses what it needs, whereas the maximum static friction is based off of that breaking point analogy. And now we have enough information to put everything together into an example problem. So here in Rapid City, we have a circular exit over by the interstate, exit 57. And throughout the years, I've seen the speed limit for this exit change. At one point, the speed limit was upwards of 50 miles an hour. And then one day there was an accident and they brought it down to 35, and now I think it's down to 25. So let's just say within the last decade they've reduced the posted speed for this exit by a half for safety issues. And so let's take the first value as our velocity, and in this case we would have to convert our miles per hour to meters per second. So you might have to look up in the appendix of your book or Google it as to what your miles per hour conversion is going to be. And let's see here. That's not right. Well, I'll just do this on the screen then. So for every 1 mile, you get 1.6 kilometers. For every hour, you get 3,600 seconds. For every 1 kilometer, you've got 1,000 meters. So long story short, we have to divide by 3 points, or I'm sorry, not 3.6. We have to multiply by 1.6 and divide by 3,600. That's not right. What did I do wrong here? Oh. So 1.6 kilometers per mile. That's right. We've got 3,600 for the seconds. That is correct. Oh, I forgot my my 1,000. There it is. 1.6 times 1,000 divided by 3,600 times 50. So this is coming out to be just a little over 22 meters per second. There we go. So that's our speed. And if you've ever taken this particular exit, it's a pretty big exit. You could easily fit a football field in there. So we'll say that the radius is 50 meters. And if you were to take the exit at the 50 miles per hour, what would you experience for a centripetal force? So that centripetal force will eventually be related to the friction, but for right now, I just want to know what's the centripetal force. And for that, we'll start with solving for the centripetal acceleration. So we're going to have 22.2 squared over 50. So I'll square the answer that I just had in my calculator, divide it by 50. And this is 9.87 meters per second squared. So as you go around this exit, you are effectively feeling the pull of gravity towards the center of that circle. And the only way for you as an occupant of the car to travel around that circle is to have basically the car, the seat belt, the side door to constantly push on you with your equivalent of your weight. So not only would you feel your weight pressing down on your seat, but you would feel your weight pressing against the side of the car door. And that can be kind of dangerous because if you're constantly pressed up against the door, you could run the risk of the door popping open, and that could be bad. But this also implies that the only way that your car can continue to push you towards the center of that circle is if there's a gravity force pushing the car towards the center of the circle. And so over the years, they've reduced that speed limit to half of its original value. Well, what would happen if you reduced the speed to half of its original value? In that case, the centripetal acceleration would be reduced to 1/4 of what its value was. Now, why is it reduced to 1/4? Because you have that squared value of the velocity. So if we cut the velocity in half, that effectively turns into a 1/4 relation. And so now having this kind of acceleration pushing you towards the center of the circle is nowhere near as extreme, and it's far safer because having the friction between your tires and the road provide you with that much acceleration versus that much is going to be much easier to achieve, especially in poor weather conditions like ice, rain. If there's some kind of gravel on the road, that can affect the friction. But let's put this into an actual friction problem. If the static coefficient between your tires and the road are 1.2. So given the current driving conditions, this is the coefficient of static friction between your tires and the road. What would be the maximum velocity that your car can have on this circular exit before you lose control? We have our static friction force, which is the only force that is contributing to our center-seeking motion. And because we're trying to max out the velocity, we're going to place our velocity and radius terms in here. Because I'm trying to max out the velocity, that means we're trying to max out the static friction force. And that's actually kind of good for us because we have an equation that tells us what that maximum static friction force needs to be. It's mu s times n. But that means I need to know what the normal force is. So we come back up to the side view that we had drawn. The normal force, assuming that the road is flat and horizontal, the normal force is just equal to the weight of the car. And now we see that the mass of the car doesn't matter. So it doesn't matter if you're driving a small compact car or an 18-wheeler. As you go around this exit, if everybody has the same coefficient of friction between their tires and the road, then everybody's going to lose control at roughly the same velocity. Now, not everyone is going to have the same conditions because not everybody has the same kind of tires on their vehicle. Some tires may be new, some tires may be bald, some tires may be all weather. But now we have an algebraic expression for what the maximum velocity can be. So we have our 1.2, 9.8, and 50. We'll plug all of that into our equation and our calculator. Square root. And I have 24.3 meters per second, which, and I just threw these numbers out there, but if we compare that to the old speed limit that they used to use, that's not that far off. And so that kind of explains why I was driving along one day and I saw the remnants of an accident up here, is that this was probably too fast for a certain someone that was driving, and maybe their tires weren't the best, or maybe the coefficient of friction had dropped for some reason, rain or snow, and they ended up hitting the wall of the exit, and you saw a bunch of scrape marks and black marks from tires that had rubbed up against the wall there. And it was a few days later they changed the speed limit sign. Now, one thing that I've been neglecting to comment on is right here. Every time we've had a square root, I keep writing in that there's the plus minus relationship. And let's see where else we've had that. We had that here with the velocity and the tension. We also had that with the velocity and the normal force. So does that plus minus mean anything in terms of the physics? Well, the whole time we've been asking for values of speed, and technically speed is supposed to be the absolute value of velocity. But there is a physical use for that plus minus in all of these problems. Let's go back to, actually we can even go back to the gravity case, because we had this show up in the gravity case as well. There's a plus minus there. All that plus minus means is that you can achieve this motion by traveling that way or that way around the circle. Likewise, you can achieve the this daredevil exhibition by traveling that way or that way through the loop. You can achieve the rock on the string by spinning the string around that way or that way. This is what the plus minus means out of each of these expressions. And since we've been dealing with speed, we've just been sort of washing our hands of that minus sign that comes out of the square root. But it is impossible. It is responsible for me to say that this situation can happen whether you are traveling the exit this way or that way. Obviously, you don't want to go that way because then you're entering the wrong way on the interstate. You're going to cause an accident. So we now have examples of all four of those forces as they pertain to centripetal motion. I have no doubt that I've gone over time on this video, so I apologize if it's too long. But we've now finished the chapter, and we are ready to proceed on to chapter 7. So I will see you then.